All right, we're on to our next problem. We want to find the volume that's above this cone and below this sphere. Hopefully you recognize this as a sphere instantly, and hopefully you've not forgotten that this is a cone. Let me just make a couple of quick comments. If you square, let's write this in red, and then I can erase it maybe. If you square this equation, you get z squared is x squared plus y squared. And if you think about it, if you graph this, that equation, you get a cone opening this way, and opening down as well. And so this is what we talked about earlier. The full cone is sort of this double cone. We're taking just the positive square root, so that's just the top half. So our graph is only going to be the top half, and then sitting on top of that cone is going to be this sphere, the top of this sphere. So it's going to look like an ice cream cone. I already had it sketched, so I'll sketch it there. Maybe I'll make it a little bit bigger. I tried. It didn't like to be made bigger. Let's try again. I'm going to waste a lot of time, so let's just stop. Hopefully you can see that. So I've got the cone opening up. Here's the sphere, and that's what it looks like. The radius there, I have a little root 2 floating. That's supposed to be the radius off of the sphere. This radius right here is root 2. All right, so let's see if we can set this thing up in all three coordinate systems. This is going to be epic. It's going to be fun. Here we go. So for part A, we're asked to do this in Cartesian. So I'm going to go ahead and write down my integrals. Somehow just writing down blank integrals, at least I've done something. And so I'm going to put a 1, and then I have to decide what order I'm going to go. I hope it's immediately clear to you that you really want to view this as a type 1 triple integral. You want to cut it along the z-axis first. It would be a disaster to try to go the other way because you're hitting all these walls. You could do it, but it really makes a lot more sense to go this way. So I'm going to go from z equals the cone up to z equals the sphere. Hopefully I can solve the top half of the sphere for z. I certainly can, actually. If I do that, solving this equation for z, I get z equals, I'm going to take the positive square root, 2 minus x squared minus y squared. And so now I know that I'm going to go ahead and write a dz down. Z is going from the cone, which was z equals the square root of x squared plus y squared, up to the top half of the sphere, which is 2 minus x squared minus y squared. Now I got to figure out the next part, the projection into the xy plane. You can see it's going to be a circular projection, right? That should be somewhat clear to you. How do you find it precisely? Well, you want to set the two curves equal to each other, or you can plug one into the other. So I'm actually going to plug this surface into the other one. And when you do it that way, it becomes pretty nice what happens. You get an x squared plus a y squared plus the radical squared, so you just get a 2x squared plus a 2y squared equals 2. You guys see what happened there? The z squared becomes the radical, and the radical goes away. So this is just the unit circle, x squared plus y squared equals 1. Maybe we'll go ahead and graph this just to remind ourselves how it goes. That's good enough. Okay. Oh, it's kind of off. Oh well. So I can cut this any way I want. I'm going to cut it vertically first. So I'm going to solve the unit circle for y, and I'm going to get y as plus or minus 1 minus this, x squared. The bottom half is the negative square root. The top half is the positive square root. Hopefully you can't hear the gargantuan dump truck driving by right now. It's kind of loud. Oh yeah, they're making really good progress on the entrance too. I actually drove in on the new entrance today. They've closed the other side down, so I'll try to post a picture of that for you guys at some point. Anyway, I'm getting distracted, as always. So now I'm just going to set this double integral over the projection, set it up, and we're going to think of y as going from negative square root of 1 minus x squared to positive the square root of, whoops, that should be a minus there, minus x squared. And then x goes from minus 1 to 1, and then we cut it y first, so dy. dy dx. All right, that's it. Now, pause for a moment and just realize how unpleasant this is going to be. It's going to be awful. There's going to be radicals flying everywhere. Very, very miserable. It's Easter. let's try and keep life somewhat positive, especially with all that's going on. Let's try to set things up in the other coordinate systems before we try and evaluate this. So let's go on to cylindrical, and let's see if it goes any better. Looking at this, it's actually going to be very similar. The initial setup and the projection are actually both the same. So I want to go ahead and redraw my picture, and I'm going to go ahead and redraw the projection. Also is going to be just the unit circle. It's going to look something like that. Just realize when I'm doing cylindrical coordinates and I'm going to rotate around the z-axis that I'm still going to make the first cut is a z cut. So you're going from the cone to the sphere. The only difference is the formula for the cone and the formula for the sphere become significantly cleaner. So let's go ahead and write down the integrals. I can always at least do that, right? Instead of a 1, I'm going to have an r, and then I'm going to have a dz, dr, d theta. And I can see that z is going to go from the cone. Look up at the formula for the cone, radical of x squared plus y squared. But when we switch to cylindrical, x squared plus y squared is r squared. So z goes from the square root of r squared, which is just r, right? The cone is just r. Technically, it's absolute value of r, but r is positive, so it's just r. And then I want to go up to the sphere. Well, look at the formula for the sphere. The top half of the sphere is radical 2 minus x squared minus y squared, and that simplifies to just radical 2 minus r squared. And then now you're looking at the projection into the xy plane, and you're realizing, oh, that's just the unit circle. R goes from 0 to 1, and theta goes all the way around. So I've got it. That seems a lot more reasonable. Some of you are looking at that radical thinking, I don't know, but maybe we'll be able to do a u sub with that r. It's very likely that we will. And we'll see. Let's look at the spherical integral before we choose which one to evaluate, because maybe the spherical will be easier, maybe not. I would like to point out to you before we go on, I should have done this at the beginning, looking at this problem, my hunch is this is going to be cleanest in cylindrical, and the reason is there's symmetry around the z-axis. But as you'll see in a minute, spherical is going to work very well as well. So let's work it out and see how it goes. For spherical coordinates, I'm going to go ahead and write this down. Integral, integral, integral. I'm going to have a rho squared sine phi d rho d phi d theta. And now I just have to figure out what's happening. And in some ways, rho is the easy one. You can see that rho is going from 0, and you go all the way out until you hit the edge of the sphere, and the sphere is the distance root 2 away from the origin. So rho, the distance, goes from 0 to root 2. That one was pretty easy. I think it's also clear that theta is going to go all the way around. So theta goes on the outside, goes from 0 to 2 pi. It's just this phi. Phi is going to start on the positive x-axis and swing down to the cone. So you can immediately tell phi is starting at 0. It's just what goes there. So what I want to do to show you where the phi comes from is actually, I'll write it, I'll squeeze it in up here. And I'm just going to look at this, a side shot of this. So let's make this maybe the z-axis and the y-axis, and this is my cone. And let's go ahead and think about the point where the sphere hits the cone. You know then that this distance is root 2, this angle is phi, and this distance across the top, what is that? Well, we saw before the projection down into the xy plane was the unit circle. So you actually know that this is 1, and that's the key, because now I can tell you that sine phi is what? Opposite over hypotenuse is 1 over root 2, which is root 2 over 2. Let's give ourselves some more space. I'm feeling claustrophobic. And now I know what phi is. Phi has to be pi force, which probably you could have guessed pi force, but we don't like to guess. In fact, we very much don't like to guess in a mathematics class. We want to be able to see why things are what they are. So that is the setup. And now we have to pick. And I'm going to claim that really cylindrical and spherical are going to be pretty similar. You will have to do a U substitution for cylindrical. It's certainly the picture suggests cylindrical with the symmetry, but it also suggests spherical because there's a sphere involved and everything is happening under a sphere. So I'm actually going to go with spherical. I think in this case it's going to be the easiest to integrate. I'm not going to work it all the way out, but actually the work that we did before, let me scroll up, the work that we did right here is the same work, you just have different bounds now. The bounds have changed. So I won't work it out with you. I don't know what I just said. I probably said that I wouldn't, or who knows what I said, but you're going to get 4 pi thirds times root 2 minus 1. So I'll leave it to you to check that one. And then if you're up for a challenge, why don't you pause the video and work it out this way as well, doing U substitution. Notice the theta, you can immediately peel off this integral as just 2 pi, and you're down to just 2. Integrating z, you're going to get z, plugging in the bounds. It's really not going to be bad at all. I would really encourage you to give it a whirl and see how it goes. Just for time's sake, I'm not going to, but please do that one actually. That's officially assigned by me as an unofficial exercise. So let's stop the video here before I make you sick scrolling, and then we'll go on in just a minute with one more example.